Hi, my name is Mariah Kim. We're talking about the Hardy-Weinberg equilibrium. So in this video, our mission is going to be to find the genotype and allele frequency before and after selection occurs. So now let's take a look at my population. I know that homozygous dominant individuals are going to have a long tail, heterozygous individuals are going to have a medium-sized tail, and homozygous recessive individuals are going to have very short tails. So now let's calculate my allele frequency before selection. So in order to find the big A frequency, I'm simply going to take 54 and multiply it by 2 to calculate for each big A present in the genotype. And then I'm going to add 74 to calculate for the big A present in the heterozygous genotype. I'm then going to divide this total value by 304, which is simply the total number of lizards, 152, my population, times 2 in order to count for each allele present. I'm going to follow the same pattern in order to find the frequency of little a's. So what about the genotype frequency before selection? Well, this one's a little bit easier. So in order to find the frequency of homozygous dominant, I'm simply going to take 54, the total number of individuals with this genotype, and divide it by the total number of lizards in my population. And I'm going to follow this pattern in order to find the frequency for the other genotypes. So about the expected genotype frequency? Well, this is when my equation comes into play. I'm simply going to take p squared in order to find the individual's frequency for homozygous dominant, and my P and Q are denoted over here as found before. I'm going to continue to follow the equation for the rest of the genotypes. Now, how do I even know that I'm in equilibrium in the first place? Well, first of all, the following assumptions have to be met. I have to have an infinitely large population so that genetic drift cannot occur. I also need to have random mating, which means that a female cannot prefer a certain phenotype for her males. There can also be no selection, no migration, and no mitation. So now that my assumptions have been met, let's take a look at my chi-square test. So after I collected this and have my value here, if it is less than my critical value, then I know that I can fail to reject the null, in which the null is the population is in Hardy-Weinberg equilibrium. But what happens if we're not in equilibrium? What happens if I have an invasive species introduced, a hawk that targets long-tailed lizards because they're the easiest to spot? Well, now let's take a look at this table over here. I already wrote down my initial frequencies as calculated before, and now I can determine my fitness. Well, I know that short-tailed lizards are going to be the most likely to survive with a frequency of 1. My heterozygous individuals are about the middle with a 0.8 fitness, and then my homozygous dominant individuals at 0.6 are the most likely to die. So my unadjusted survivors is simply going to be the initial frequency times the fitness. To find the genotype frequency after selection, I'm then going to take the unadjusted survivors and then divide it by my average fitness. So over here is the end value for the genotype frequency after selection. So what about the allele frequency after selection? In order to find the frequency of big A, I'm simply going to take the frequency of homozygous dominant individuals plus 1/2 the frequency of heterozygous individuals. And then I'm going to follow this pattern for my little a frequency after selection. So now let's compare these. As you can see, the frequency for little a is going to increase. And then my homozygous recessive individual genotype frequency will also increase until there are only little a lizards left. So when only one genotype is favored, in which the one extreme is favored, I'm going to have directional selection. I hope this helps you understand the Hardy-Weinberg equilibrium equation, and check out these sources if you have any other questions.